Now we are ready for our crystallographic restriction theorem, which I said is one of the most beautiful and important theorem of this course. What does this theorem say? This theorem says that in crystals only 1, 2, 3, 4 and 6, I am not making any mistake, 5 is missing. And 1 bar, 2 bar, 3 bar, 4 bar and 6 bar axes can be present. Simplifies our life dramatically. Otherwise, there is no limit on n goes from infinity. If there are a finite object, you can have 5-fold symmetry. Think of a regular pentagon, 5-fold symmetry. In the model making you made icosahedron, has 5 bar symmetry. So, all these symmetries 5-fold, 6-fold, 7-fold, 8-fold, a regular octagon, 8-fold axis. But you can't arrange a crystal to have 8-fold symmetry, it will not be there. So, in crystals only these 10 possible axes can be there. Five-fold is not there, 5 bar is not there. How do we prove this? The matrix proof is very simple. It will, if you have understood the matrix method, now the proof will almost appear to be trivial. So, let us do the matrix proof. Why this is so? Why is this restriction is coming? What is special about crystal which is not there in a regular octagon? Sorry?
The point groups has to exist.
Point group?
The groups has to exist in the system.
So, 5-fold is a point group, 5-fold axis is a point group. There are 5 rotations. If you consider 5-fold axis, 5 is a point group consisting of 0 degree, 72 degree, 144 degree, after that 216 degree, 288 degree. These rotations will bring pentagon into self coincidence. If you join the centroid of the pentagon to the vertices, these are the 72 degree, 1 times 72 degree, 2 times 72 degree, 3 times, 4 times and finally 5 times. So, these 5 elements 0, 2 pi by 5, 2 pi by 5, 3 2 pi by 5 and 4 2 pi by 5. So, these represent the symmetry operation. So, it is a point group and it leaves one point of the pentagon unchanged, the centroid of the pentagon unchanged. So, it is a point group, proper point group. It is not that 5-fold axis will not give you a point group. It does give you a point group, but it gives you a point group incompatible with crystal. Where is that incompatibility coming from? One thing which is not there in the finite object, that nothing is repeating. There is no unit cell, there is only one object. So, if there is only one object, it can have arbitrary symmetry. But as soon as you demand that object should repeat at equal intervals in 3 directions, that repetition, that translational symmetry is actually what is putting this restriction. So, this restriction comes from the fact that only these symmetries compatible with translational symmetry of the crystal. Which is the defining symmetry of the crystal. Crystal need not have any 2-fold, 3-fold, 4-fold symmetry. If it is a crystal, one symmetry which is guaranteed for it to have is that it should be translationally periodic. How we define crystal? We did not say a crystal which has a 4-fold symmetry. We say a crystal should be a translationally periodic arrangement of atoms. When we brought in translational periodicity, essentially we are demanding that it is having translational symmetry. So, only these symmetry rotations, only these 10 symmetry rotations are compatible with translational symmetry. Why is that? So, let us look at that. Since you have a crystal, and since you have a translational periodicity, and you have a choice to select some crystallographic coordinate system, which will be some lattice translation. Suppose this. So, this is one possible basis vector. You can have what is the difference between the blue basis and the red basis? Blue is primitive, red is non-primitive. What is the difference in the coordinates which these bases will give to the different points? For example, this point. This point will have coordinates what in the blue system? -1. Suppose if this is my A, this is my B, and this is my A prime and this is my B prime, sorry, this is my A prime and this is my B prime. So, in the blue system it is -1, 1. In the red system, half, half. Will primitive ever give you a fractional coordinates? That is the beauty, or that is the advantage, or that is the power, or that is the excellence of a primitive system. Primitive assures you that all lattice points will have integer coordinates. integer, or sometimes it is called integral, but it has nothing to do with the definite or indefinite integral. Integral here is adjective of integer. So, now let us write, suppose W is the rotation matrix. Representing, let W be a matrix representing a rotation in a primitive basis. So, you have some coordinates, some starting coordinate of some lattice point x, y, z, coordinates of the rotated point. Remember, we decided that not to write prime for rotation, but the tilde. So, initial, because if it has a rotation, suppose this was a rotation axis, suppose this is some sort of rotation axis, then it will rotate some lattice point to some other lattice point. So, this lattice point is being mapped to that, this lattice point is what I am calling x, y, z. After rotation I am calling it x tilde, y tilde, z tilde, and the matrix is doing that transformation for me. So, the matrix is W, and my basis is primitive basis. In the primitive basis, what is x, y, z? What is the form of x, y, z? Integers. So, each x, y and z are integers. After rotation, the new lattice vector which you get is also being represented in the primitive basis. So, what will be the form of these? Integers. Now, if you have a matrix which on multiplication gives you from an integer column vector to another integer column vector always, what will be the form of W? So, let us do it one by one.
W is any rotation matrix or
Any rotation, no, symmetry rotation, because it takes a lattice point to another lattice point. So, this is also a lattice, that is why they are integers. So, this is a lattice point, this is a lattice point, and this is a transformed lattice point, a rotated lattice point. And this is the symmetry rotation. The rotation will act on all vectors, all lattice point. One of the lattice point has to be 1 0 0, end of the A vector, the first basis vector. 1 0 0 multiplied by W will give you what?
at least an integer?
That is the first column. Any matrix, if you multiply by 1 0 0, you pick out the first column. 1 0 0 was integer. What do you say about W 1 1, W 2 1, W 3 1? each of W11, W11 is an integer, W21 is an integer, W31 is an integer. If they were not, then our this relationship that a lattice point goes to lattice point and in primitive basis they are integers will be violated. So, if this W is a symmetry rotation and I am working in a primitive basis, then W11, W21 and W31 have to be integers. If I multiply by 0, 1, 0, what will I get? The second column. And what will we claim or what we will decide about these numbers? Integers. So, all elements of this matrix integers. So, this matrix itself is an integral matrix. So, any symmetry rotation represented in primitive basis is an integral matrix. Integral matrix means all Wij for all values of I and j, they are integers. If that is true and if this is representing a rotation, what can we say about the trace? But 2 cos theta plus 1 should be integer. It is an amazing result. Just think about it. 2 cos theta plus 1, cos theta is a fraction and theta is an arbitrary angle, rotation angle. With an arbitrary rotation angle theta, cosine can have any value. I am multiplying it by 2, adding 1. So, it can have any arbitrary value. But if this theta is part of rotational symmetry of a crystal, then only those thetas will be allowed for which 2 cos theta plus 1 is integer. We have come to this very this is what is you are already seeing, that the translational symmetry is restricting theta. It is not letting you have arbitrary theta, because arbitrary theta will give you a non-integer. But if it is part of crystal symmetry, our analysis demands that 2 cos theta plus 1 has to be an integer. What will be the maximum integer for 2 cos theta plus 1? What will be the minimum value of n? So, what are the all possible integers n? Minus 1, 0, 1, 2, 3. What were the axes we are saying that are allowed? 1 fold, 2 fold, 3 fold, 4 fold and 6 fold, 5. 5 different axes, 5 different integers between minus 1 and 3. Beautiful result. You can just now simply work out that what do these n's stand for. So n is equal to minus 1, 2 cos theta plus 1 is equal to minus 1, 2 cos theta is equal to minus 2, cos theta is equal to minus 1, theta is equal to 180 degree. 180 degree rotation, two-fold axis. So we are happy. Two-fold axis is allowed for a crystal. Existence of n is equal to minus 1 is telling us that two-fold axis is allowed for a crystal. N is equal to 0. The main thing is done. The rest is just algebra and identify what these numbers are representing in terms of the angle. Cos theta is minus half, theta is 120 degree, fold, three-fold. N is equal to 1. Two cos theta is 0, theta is 90 degree. And finally n is equal to 2. No, not finally, n is equal to 3. We have to go up to n is equal to 3. 2 cos theta plus 1 is equal to 2. Cos theta is equal to half, theta is equal to 60 degree, 6, 4. We have exhausted everything. What will 3 give? So n is equal to 3. 2 cos theta plus 1 is equal to 3. Cos theta is equal to 1. Theta is equal to 0 degree, which is same as 360 degree, which is no symmetry. But we don't like to be negative, so we say we have one-fold symmetry. Saying one-fold symmetry is saying that there is no symmetry. Any arbitrary, any odd object, if rotated by 360 degree, or if not rotated at all by 0 degree, it will be in self-coincidence. So symmetry is not required for that. But if there is no symmetry, we take a positive attitude to life and say it has one-fold symmetry. So thank you very much.